So in HPC we face a lot of challenges now. We have a transfer time now from, let's say, the PETA area, which was, let's say, easier to reach, than now to the EXA area, which will be, let's say, more challenging because we are reaching limits of technology, reaching limits of capabilities of systems, and we cannot use anymore the traditional paradigms we used so far. So we have to work on, let's say, on the baseline of new mathematics, new algorithms, new ways of, let's say, handling parallel processing. We have to work on the energy efficiency of systems because, yes, systems will grow, but so will also, let's say, the energy consumption. Energy is, let's say, first of all, in terms of sustainability, a valuable good, and secondly, very expensive. So we have to see in how far we can, let's say, have an increase of the capacities of computers by ensuring that we don't have a too massive increase in terms of costs and ownership. Total cost of ownership is very important. And centers are, let's say, always funded by by government bodies or, let's say, by different funding agencies. And we cannot simply, let's say, increase that funding that much just to cover all these things. So we have to work on the technology. We have to work on things which reduce our total cost of ownership, and of course we have to work on the efficiency of systems so that at the end the customers or the users of the system also benefit from a quicker system. So what we learn in global system science that you have models, and models can be very easy or very complex, and it's the same thing, let's say, for computing. You have, let's say, some smaller machines which can handle easy problems or easy, let's say, questions. But the more we want to go into mapping reality to the systems, the more we need complex structures of systems and science to really be able to map this one-to-one to the system. So at the end, the project, or let's say the problems can consist of a variety of parameters. And I can, of course, go for 4 parameters. Then I have, let's say, a probability of a result to happen, which is probably, I don't know, 50–60%, or I can integrate much more parameters and can increase the probability. If we are now talking about decision-taking processes, we need the highest probability possible, which will be never 100%, because at the end it's still a simulation and we are mapping, let's say, somehow the real world to a system. But the more parameters we can put in, the more challenging the overall, let's say, problem gets, and the more, let's say, system resources and capabilities of systems we need to have. Even if it's a new community, or let's say a newer community, which of course doesn't have the decades of experience in writing codes to solve problems. A lot of the problems in the global system science domain can be mapped to, let's say, a combination of different, let's say, applications which already run on HPC. So we can talk about, let's say, or we can imagine it as some sort of core application which is in the middle, which then addresses my certain problem. Let's go, for instance, something like a refugee movement. Refugee movement is, let's say, quite simple because people move from one place to the other. The question is, why do they move and where do they move? So you can put in, let's say, climate issues, climate parameters. Climate simulation is perfect for HPC because it scales up to the highest level. Then we have to think about the economic value. Where do people want to move? You don't want to move from one crisis area to the next crisis area, so you go to another place where you think you're safe. Which is the next safest place where you want to be? And we've seen this, let's say, in reality, how it happens. And the prediction of such things then, let's say, consists of, let's say, the combination of a variety of different sub-simulations which all produce data. The produced data is big, partially very big. And you have also to integrate this in new simulations. You have to, let's say, a cycle of reverting this, updating this on base of new data gained. And this is then something which is only possible in really big systems and effective systems with quick networks, quick processors, quick memory, to be able to have in a feasible amount of time a result that really helps you to take decisions, or at least to, let's say, estimate the situation as it will happen.